So good afternoon, one and all present here. Today, so in PhD Research Scholar talk, today we having a discussion about my recent research paper. So that is nonlinear MPC with enhanced state estimation using UKF for interacting variable area hybrid process. So I am Satish Kumar. I am from Department of Electrical Engineering, NIT Calicut. I am a research scholar here, and my research supervisor is Dr. Kangalashmi ma'am. She is assistant professor in Electrical Engineering Department, NITC. Okay. So this is my recent research article. So it is published in IEEE Access this August edition. So these are the content we are going to see today. So we have a little bit introduction and mathematical model, and the objective of the proposed work and methodology, results and discussion and references. So based on the research and the research article which I published, so that is what we are going to discuss today. And introduction is concerned. So most of the process industries use variable area tanks, so such as conical, spherical tanks. So a unified control strategy for whole operating region remains an open research problem. So either a single tank or interaction is there, but the area is going to be the same. But the variable area types of tanks and its controlling is still tedious nowadays, and it's still an open research problem. So we are performing an experimental validation with the help of the controller design which we design. It is going to be implemented here in NIT, and we find some solution. So that is what we are going to discuss it today. So we are using nonlinear model predictive controller, NLMPC, with Unscented Kalman Filter. So for a nonlinear lab scale interacting two tanks hybrid process which we are having, which provide a dynamic model predicting capability and better compensation towards nonlinearities in the presence of continuous measurement noise. So first we have to see what is this interacting two tank hybrid process. So generally we from here onwards we call it as ITHP, where this experimental hardware setup, as you see here, so this having this two tanks which is in variable area, so which having an interaction between these two tanks, as you see in this, there is a hand valve is there. So due to this interaction, there will be a high nonlinearity will be possible to produce. So these type of tanks which we used in many industries like chemical and pharmaceutical industries, food and beverage industries, water treatment plants, petrochemical and oil industries, cryogenic application, power industries. In many areas, these type of tanks are available. And future of this experimental setup we are having, so we can introduce a heavy nonlinear dynamics and dominant time constant delay and minimum and non-minimum phase systems, time varying uncertain systems, square and non-square process we can introduce in this setup. So in this IDT-HP setup, so we are designing a nonlinear model predictive controller with UKF. So how it going to perform even in the heavy nonlinear dynamics, how it can perform well. That is what we are going to use in our lab scale setup, right? So these are the specification. So it is a 70 centimeter tank. This conical tank which you are seeing, it is a 70 centimeter, and the spherical tank which is a 50 centimeter tank. Similarly, the radius is 30 and 25 respectively. Similarly, there will be a interacting manual valve between these two. Okay, and this experiment is considered we are using this bottom interaction valve for interaction purpose. So this is a mathematical model we developed. So as we see, there is a two tanks, this conical and spherical tank. So based on this tank, we are designing a mathematical model. This mathematical model consists of this area of the conical shape. Okay, so based upon the input U1, and we are having an outlet here. So that is going to be this portion. So that is going to be always whatever the effluent or fluid is coming inside is getting drained through this. So similarly, again, we having a interaction valve is there. This HV12 due to this interaction valve, and based upon this coefficient, whether this height of the tanks is getting deferred Based on that, there will be the coefficient of this manual ball, right? Similarly, for spherical tank, so we designed this mathematical model for this experimental hardware setup. Okay. Next, we are coming to this controller design. As the controller design is concerned, so we having a we are planning to design a controller which should carry the our constraints. Okay. So as well as our control objective should satisfy, and also it reach the set point. So thus all these three should be as a pack. It should satisfy, the controller should satisfy all these three, right? Based on that, that manipulated input should come to the nonlinear system. And as we know, the nonlinear system is nothing but here is IDDHP, that two-time hybrid process, where the measurement is continuously measured and it is getting feedback and given to this controller again. And our idea is we are bringing this UKF here. So this Unscented Kalman filter is going to be like an observer. Similar to observer, his Unscented Kalman filter will estimate the states before it's going to this controller part. It will estimate the states, and based upon that, controller should take action. So as we know, we having a two inputs. One is from the feedback and another one is from this Unscented Kalman filter. As we know, this Unscented Kalman filter, here we are using this predictor corrector approach. So where every steps there will be a prediction, in every step there will be a correction. So this predicted and corrected estimated state is given to this controller, right? So for this constraint handling, explicit constraint handling, we can go for MPC design. So the MPC design is concerned, it will linearize the nonlinear model, and it will optimize the values, and it apply, and it will repeat. So up till the receding horizon, it will use a mathematical model to predict the future plant behavior, optimizes the control moves to minimize the cost, that is tracking error and control effect combinedly, and it applies on the only on the first move. Okay, so one step ahead prediction we will say, then repeats at the next step. Likewise, it will for each step it will take the control action. So generally we will having the nonlinear model for MPC, but it will linearize the model. We can go for this state space type of models we can use for MPC, and we should decide the prediction horizon, control horizon. As you know, prediction horizon is how far ahead the controller predicts, and similarly control horizon, how many future moves the controller can handle. So that is what the prediction horizon and control horizon. And we have to define a cost function, usually quadratic type of cost function we will define. That is the error plus input penalty. That is going to be your quadratic cost function. And we will having a constraints, and this part is constraint. We having a constraints in terms of actuators. So in this, as we see earlier, that this two-tank hybrid process uses control valves. Okay, so that is the actuator is having some limits. There will be a safety restrictions also. So it can't be opened fully. It can't open suddenly. It should not open or close. So that quick movement should be avoided. So there should be a smooth transition also. That is also more important for industry purpose. The constraints is there. So combining all this, MPC can be designed. As you see, this MPC for here is we are using up to prediction horizon as 15 and control horizon is 10. And this mathematical model we designed for the this two-tank hybrid process, and we have to find the optimal cost function. So the start function based upon the output and the mathematical model, the mathematical model output and the actual measurement process. So by combining all this, we will define a cost function. Right. Next is NLMPC. So as we know, this NLMPC, what is the advantage of MPC and NLMPC? NLMPC uses the nonlinear model directly instead of linearizing using some Taylor expansion or something. So it predict the future behavior using a nonlinear model itself and solve an optimization problem over a prediction horizon. Apply similarly it will apply the first control action and repeat to the next step. Likewise, it will move on. So till the up to the receding horizon. So generally, this nonlinear dynamic model for NLMPC we use ordinary differential equation, state space model, or sometimes black box approach. As you know, black box approach is based upon the input and the output. We will find the model of the system. So that is the black box approach. And similarly, here the cost function is to minimize the tracking error as well as the control effort. So it is combining of this cost function is combining of two things. This E stands for the control error associated with the controller weights, error weights, and we have to minimize this cost function. What is this del U? It is nothing but the control effort. So that is associated with the weights. Okay, so we have to minimize these cost function such that we have to find the manipulated input to the nonlinear system. And the next part we are moving to this UKF. So what is this UKF? So as we know, this EKF, UKF or these Kalman filters, we having many types of filtering techniques. This here we am using this UKF. Why? Because of instead of if we consider this EKF, it will instead of the UKF, instead of linearizing, UKF propagates a set of sigma points through a nonlinear system. So what is the sigma points? These points are meant by it capturing the mean and covariance of the systems. So this sigma points is more accurate than the Taylor series expansions used in other Kalman filters. So approximation is very accurate. So up to second order for any nonlinearity. So here we are using this UKF, and we need to see this parameters. As you see here, there will be parameters for measurement noise covariance and the process noise covariance is alpha, beta, and all these should be the parameters should be, the value should be have to be finalized based upon we used some nonlinear optimization techniques. So to find these values, and similarly we have to give the constraints for NLMPC. So we have to state the output constraints. As we know, this how much the output del U should change. Del U is nothing but the control effort that is the output the manipulated variable is giving. So how much it should vary, that should be, we have to constraints we have to give, because as I said earlier, more the value changes, it will affect the actuator. So it should be controlled in between. It should be having some constraints. And what are these tuning parameters of this NLMPC? As we know, this tuning parameters are prediction horizon, control horizon, and there is output variable weight and manipulated variable weight and sampling times. So all these things should be, we have to find those parameters such that we can get a good output in our final real-time setup. So these are the simulation results, which is without the Unscented Kalman filter. So we studied with the simulation, the same IDHV with the help of this ordinary differential equation, and we found the output and control responses of NLMPC without this UKF. So without this UKF, how it is performing. That is what we studied. And we found this MPC and NLMPC is performed very nice. Both compared to MPC, NLMPC is performed very nice. And these are the tables such you see here for various operating point, because our idea is we have to find a unified control strategy. So not for a single tank, not for a particular area, and we are trying to find a unified control strategy that is that will work well in whole entire operating region. That is what our idea. So we found that this MPC compared to MPC, NLMPC performed better. Similarly, this for this conical process and the spherical process, we tabulated here. As you see, this NLMPC, as you see, the from every aspect, the NLMPC performed better in terms of IAE, IAC. So IAE is something what integral absolute error and square error. So in both the performance indices, NLMPC performed better. And similarly for spherical process also, this NLMPC performed better compared to MPC. So, and similarly, this time response characteristics, the rise time, peak overshoot, and settling time, rise time, in every aspects, the NLMPC's performance is better than that MPC. So that is what the findings we found from simulations. So now we will have different cases. As we see, the as a variable area tank process having we having two tanks. So the H1 stands for the height of the conical tank, and H2 is the height of the spherical tank. So we see in this case, the conical tank having more height. That is the water storage we are saying. The storage of water is higher compared to this spherical tank. In this case also, NLMPC performed better. And similarly, there will be a second case, H2 and H1. That is H2 is more. That is the spherical tank height is better above the value of conical tank. In that case also, NLMPC performed better. So that is what the simulation finding we found. So similarly, now we are introducing a disturbance. So in simulation, we introduce a disturbance with the injected impulse disturbance we gave. So sudden change we are applying that that for impulse disturbance compared to MPC, NLMPC performed better, as you see from the graphs. Okay, so there will be a the control effort is somewhat higher compared to the MPC, but here there will be a higher overshoot which you found in this NLMPC. Okay, and similarly, this is for conical process and this for spherical process. So in this process also we injected a disturbance and we found this there will be more control effort in NLMPC, okay, compared to this MPC. So as we see this time response and characteristics and performance indices, okay, this IAE values NLMPC is somewhat reduced for 0 to 20 centimeters. So every instance we are comparing, okay, and the disturbance occurred area we also checked, okay, and we found that there will be slight variations compared to the servo response, disturbance response. The NLMPC somewhere there will be a performance reduction is there, right? So we will compare the control effort. So for both the cases, so the conical tank level is higher than the spherical tank. In that case, we compare, okay, for MPC and NLMPC. So NPC and NLMPC, there will be a slight increase in control effort, as we say. So control effort also should be minimized. That is what the objective we having. But in control effort, as you see here, there will be increase in the control effort, right? So now, for under disturbance condition also, so there will be a slight increase in the IAE, whereas IAC is somewhat reduced. So this is what the conclusion we are coming. So the control effort is somewhat increased values in the NLMPC we have found. So again, we will check with some other characteristics. So as we know, the real-time environment is always surrounded with noise. So we introduce a noise characteristics. So we introduce a noise. So Gaussian noise generally. So here we introduce a Gaussian noise for simulation purpose, and we observe that simulation result, as you see here, there is a need of some another observer, so that we have to reduce this measurement noise. So we are using UKF, Unscented Kalman Filter. This Unscented Kalman Filter reduces the measurement noise, okay, and it will effectively work with NLMPC. So as we see earlier, so with the help of these UKF, this is the presence of UKF, NLMPC performance is getting improved. So that comparison that is plotted here. So here, as you see, so here the estimated values of UKF, as you see here, due to the presence, even the presence of the noise, it is getting reduced. So in this portion. So with UKF, NLMPC performance can be improved. That is what the conclusion we are coming here. Okay. Similarly, we are seeing the regulatory performance. As you see, in the regulatory performance, so the NLMPC with UKF performed better from the results, as you see here, by reducing the measurement noise. This NLMPC's values is precise towards the set point. Okay. So what is the conclusion? Without the UKF compared to MPC and NLMPC, the control effort values of NLMPC is higher. So we are introducing a UKF such that in order to bring the precise values. Okay. So for that, we are using this UKF along with the NLMPC. Right? Okay. And these are the performance indices. As you see here, so various performance indices of NLMPC and MPC with UKF for conical process and spherical process. As you see here, compared to the earlier, now the performance indices and the response characteristics both are improved very well. So in both the operating region, these NLMPC and MPC, the NLMPC performed better. So that is what the conclusion we are coming here. So even under the disturbance and the measurement noise, the NLMPC performance is better compared to the MPC. As you see from the IAE, ISC values, the values of NLMPC is getting reduced. That is, the error values control is getting reduced, as seen from the performance indices of the. Okay. So as we know, this ideas we are by simulation. We performed the simulation and we found the NLMPC with UKF is performed better. So now we are tried with the experimental validation. As I see earlier, there we used this two-tank hybrid process, interacting two-tank hybrid process. The same process we used for experimental validation. So initially we performed an open loop study. As you see here, this open loop study, both the spherical and the conical tank level, it is somewhat settled, but not fully. Okay, it is still so the settling value is not reached perfectly. But anyway, it performed somewhat better. So as you see from this open loop response in the conical and the spherical tank. So based upon this open loop study, we are designing this NLMPC with UKF. Okay, and these are the various experimental validation for various controllers. So we start with the PA controller. So you know the fundamental controller. We compare it with MPC, NLMPC, and NLMPC with UKF. So as you see here, the graphical the graph shows. So the FPA having large overshoot, those overshoot is got reduced with the help of this NLMPC. As you see here, even though the overshoot got reduced, at the same time, the Gaussian noise, the noise which is produced through the sensors, that is also get reduced. And the control effort is concerned, that is also get reduced by using this NLMPC with UKF. Similarly, as you see here, so this is for conical tank. In the conical tank also, this NLMPC with UKF performed better compared to this other controllers, NLMPC, MPC, and PA. Right. So this is about servo response. So now the servo response is extended by changing the interaction valve settings. As you know, there is an interaction valve there between these two tanks. So we change the interaction valve settings for different percentages, 30, 45, 60% for different percentages, how we perform. In all the different percentage of valve settings positions, NLMPC performed better. And these are the real-time validation results. So compared to PA, NLMPC with UKF is performed better than all other controllers. So in all other controllers, this IAE, ISC control effort in all the values, it performed better. Right. Now we go for this regulatory performance. So we are introducing a disturbance. So how we are introducing a disturbance? So we using a graduated container and some 5 liters of water is suddenly added to one of the tank, and we check how the for injecting this type of disturbance, how it performing. So that is what the regulatory performance we did here. So I supplied some around some 10 liters of water. So almost from 25 to 35 centimeter, as you see, sudden increase in the tank height due to the injection of water happened. So this NLMPC with UKF, as you see, it is taking the control action, and it was due to this presence of this control action. So there is nothing but the U1 is getting reduced means nothing but the input is getting reduced. By reducing the input fully to make the tank to settle. So it will try to settle, and for compared to this NLMPC with UKF and compared to other controllers, NLMPC with UKF performed better. As you see, the control effort with the other controllers, NLMPC with UKF is performed better, as well as it also reduced the measurement noise of the controller. So the measurement noise of the sensors get reduced by with the help of this NLMPC with UKF. So this is for conical tank. Similarly, for spherical tank also, we introduce a sudden disturbance by adding a water, some 10 liters of graduated container. We suddenly introduce a water inside the tank. So due to this presence of this NLMPC with UKF, it performed better, and it will try to settle as we give as the set point which we decided here. Right. So these are the servo and the regulatory performance. And all these three performance indices and all these external validations set up, we can come to the conclusion of this NLMPC UKF with UKF performed better than the other controllers. So that is what the experimental result we brought. Right. So these are the comparison of this various controllers. So we are comparing this various controllers with NLMPC with UKF, and its performance is comparatively better, and the measurement noise also got reduced. That is also by seeing the graph itself, it is evidently we can see them. Okay, so this is what the findings we found from our experiment, right? And this is the conclusion. So a unified control strategy we proposed, even across the challenges in the variable area tanks, so which remain unexplored. NLMPC with UKF it will handle the non-linearities and measurement noise of the IDTHP. Okay, so that is both the conical and the spherical tank, and with the help of IAE, ISE, and CE. So we are estimating. We come to conclusion that with the UKF, NLMPC performed better. So that is what the conclusion we brought here, and it will track the desired set points even in the by mitigating the disturbance as well as the measurement noise in the regulatory studies. And further, the robustness of the NLMPC with UKF is validated with our IDTHP setup. And in both the IDTHP setup, we produce the reduced IAE, ISC, and CE value compared to PA, MPC, and NLMPC. So by means of these, we conclude that NLMPC with UKF was more robust in the presence of non-linearities and measurement noise, along with the process interaction than NLMPC. And this is a research article we published, Nonlinear MPC with enhanced set estimation using UKF for interacting variable area hybrid process. So myself, Sadish Kumar Swami, and Kanalashi, my research supervisor, and Selva Ganeshan sir, the senior member of IEEE from IIST, and Rishikeshwar Kumareswar, another MTech scholar here. Right. The future scope is concerned. We can put focus more by reducing the computational complexity for large scale systems. So by integrating this NLMPC with heuristic optimization, what is this? Why is this needing? This computational complexity plays a vital role. So while performing the real-time experiment, we found that it is very difficult for process this NLMPC algorithms in our computations while doing computation, especially in the real-time environment. As we know, we having a data acquisition card. So this data acquisition card and the processing capability of a computer, everything should be higher. Then only we can process quickly and we can collect the data. So that is what the future scope we are moving for this some heuristic automation techniques such that to reduce the computational complexity by some ways it should be reduced. And we didn't go for this parameter uncertainties. Parameter uncertainties in the sense of by changing the diameter or radius of the tank or the coefficient, wall coefficient, that is the interaction, everything that the parameter uncertainties with the process disturbance and model mismatch. So making these all this as a constraint, we have to design an NLMPC. That is what the future scope we are proposing. So all this we are working forward, and these are the future scope. Okay, and this is the publication we published this last August 2025. Okay, and these are the references we used here. Thank you.